Okay, so today we're going to kind of start with the bidirectional equation in the body that adjusts based off of what's being changed or influenced. So we have the this end of the equation is showing the hydrogen and the bicarb. This is the carbonic acid. It's an intermediary step. It's, according to Dr. Schaefer, it just happens really quickly. And then as you see here, we have the H2O and the CO2, right? So H2O is in excess in our body. We always have a bunch of that. So then if our CO2 levels change, that's going to affect things, just as well as if our hydrogen levels in the body change, that's going to affect things. So the normal pH of our blood plasma is 7.35 to 7.45. Might vary based on your school, but this is what we're going to use. And so the body always tries to maintain homeostasis and trying to stay at this level because acid can denature proteins, and we don't want that in our body. So that's why we're always trying to maintain this 7.35 to 7.45. So, okay, and then down here you see the hydrogen and the pH and what's going on there. So here we have just kind of expressing our inverse relationship between hydrogen and pH. So the easiest way that I learned it is that the relationship is an inverse relationship. Therefore, if we have high hydrogen, we have low pH. And if we have low hydrogen, then we have high pH. And then you just need to understand the pH scale and the, here, we'll just do it real simple, real quick. We have 0 to 14, right? Boom. And then the middle is 7. And so that's going to be neutral. And then another easy tip here for me is that A comes before B, right? So then if you have A, that's acid. If you have B, that's base. So the lower the number, then it's going to be acidic. The higher the number, then it's going to be basic. So then you can relate that over here to our inverse relationship. So again, now we have the high pH and the low hydrogen. Well, the high pH, as we just discussed, means that it's going to be basic. And then the low pH, high hydrogen, but the low pH means that it's going to be acidic. So what's a buffer, right? Well, so this bicarb over here, this bicarb is one of the buffers of the body. There are other buffers, but this is the buffer that we're talking about. But a buffer by definition, it moderates pH change, but it doesn't prevent the change that's going to happen when an acid or a base is introduced. So it just either combines or releases hydrogen as an attempt to not allow it to be such a drastic change, but the change will still happen. All right, so now we have respiratory acidosis. Okay, so the respiratory acidosis is going to, so patients that you're going to see this in are going to be primarily your COPD patients. Could also be emphysema, and then hypoventilation can also cause respiratory acidosis. The big thing here is that there is CO2 retention, right? So that first part of our equation was, let's see, that was H2O plus CO2. And then we just said that this patient has CO2 retention. So that is going to indicate that our CO2 levels are rising. And then I'm going to write the lines as if we were going either way. Okay. And then the end result, well, the other side of the equation is going to be the hydrogen and the bicarb. Right? So there's that. With the, so okay, so again, according to Dr. Schaefer, there's the, then an easy way to look at this is we have the seesaw, right? So we have the seesaw, but this is an unbalanced seesaw because this CO2 has increased, and so it's weighed down on this side of the seesaw. So now we need to go to the right on this equation. And what's going to end up happening is that now you're going to see that increase in the hydrogen, and you're going to see an increase in the bicarb as well. Now, typically, if you're seeing this in a patient, they have gotten to a point where they can't get that CO2 out on their own. So, well, the respiratory side of it, right? Because we're talking about the respiratory. So then you're going to see the renal compensation kick in to help with this. And that's going to be what I follow up with another video on for you guys. Okay, so now we have the metabolic acidosis, right? So again, okay, so you know what? Here's a thing that I didn't really mention on the last one, but so we're talking about the acidosis, right? So acid, right? And then, so the acid means that we have that low pH and the high hydrogen, right? Because of that inverse relationship between pH and hydrogen. And again, you can see that here on this equation because you're seeing the hydrogen increase right here. Okay, so now moving on to metabolic acidosis. So metabolic acidosis has there's a couple of ways that you can get to this state, right? So you can have lactic acidosis, and then there's ketoacidosis. The ketoacidosis is going to be the more common way that you're going to see the metabolic acidosis kind of be a problem. And again, so that's going to be more prevalent with a type 1 diabetic, or you can see it a little bit with the low carb diet as well, but I'm not gonna get into that because that's a different science than what we're talking about. So on this one, you can see that I've made the note that the dietary and metabolic input of hydrogen exceeds the output. So this means that something in the body is happening, that you're getting this increased hydrogen and the body isn't able to compensate for it. So we're going to go ahead and write our equation out again. So we have our H2O plus CO2. And we're going to do our 2 arrows. And then we have our hydrogen and our bicarb. Okay, and as we just discussed, this is going to show the increased hydrogen, and and then we have the seesaw again, right? So this is going to make the seesaw like this, because the right side of the equation is heavier with this free hydrogen that's making it more acidic. So this equation is going to move to the left, and then you're going to see an increased production of CO2, and the body is going to try and get rid of that CO2 with this weird breathing pattern where they really try to blow off that CO2. I'm sorry. Okay, so because of this excess CO2, you're actually going to see a little bit of a respiratory compensation try to happen here in the form of hyperventilation. And we'll kind of cover why that would work in the next segment. So let's see, the other big thing here is going to be that the HCO3, so our bicarb right here, is really the telling factor on if this is metabolic or respiratory. So as we saw over here with the respiratory, we had an increase in this HCO3 bicarb. But in the metabolic, you actually see a decrease in the bicarb. Again, that's going to be the clue between the difference. Or that's going to be the clue to tell you maybe which one's going on. And then let's see. Yep, I think we're good there. Got the H2O, the CO2. Oh, I guess so. The other thing that I don't think I mentioned, I might have though, is that we have this seesaw again, right? And so because it initially started out from this hydrogen over here weighing down the seesaw, the equation here is going to move to the left to try and compensate. I might have said that. That's okay. Alrighty, so now we have the respiratory alkalosis, right? All right. So because we are looking at alkalosis now instead of acidosis, that's probably going to mean that our body is too basic, right? So then if we're thinking about base, what do we know about base? Okay, so base is high pH, and low hydrogen because of that inverse relationship between the pH and the hydrogen, right? All right. And then we have our equation here with the H2O plus CO2. Do our arrows. And then we have our hydrogen plus our bicarb, HCO3. Okay. Respiratory alkalosis is much more, it's less common than any alkalolytic condition is less common than an acidotic condition. It's just harder to get to this state. So with this one, it's going to be that the, again, okay, so this one is going to be mostly seen. So we're going to look at this clinical aspect right here. So clinically, it's most common from mechanical ventilation because it's this hyperventilation that's causing this respiratory alkalosis. Typically, on their own, a person isn't going to hyperventilate enough to make this alkalosis happen. So that's why the most common way to see this is going to be from the mechanical ventilation. You have to come in and reset the vent settings, but that's that's another science that we're not getting into right now. So, okay, so, but what we know, right? So if the respiratory acidosis was from hypoventilation, and we saw that increase in the CO2 because the body was retaining it, then we have, so now we have this respiratory alkalosis that's the hyperventilation. So we're going to see that decrease in the CO2 because the body isn't getting enough, it's not able to take in it's not able to produce enough CO2 faster than the body is getting rid of it with expiration, right? So, excuse me. And then, okay, so if we have this decrease of CO2, right? So that decrease is going to make our seesaw lighter on this side, right? Whee! That was a really bad seesaw, but that's okay. And then, so to balance out the equation, you're going to see a decrease in the hydrogen and the bicarb as well, because that's going to lower the weight, if you will, that's pushing down on this side of the seesaw. And that's going to help bring our seesaw back to homeostasis. Yeah. I think that's, yeah. Okay, and then because this is a respiratory problem, it's going to be solved through the renal response. Again, that's another video that I'm going to do for you guys. So yeah, so just here, it starts out with that decrease in CO2, which causes a decrease in the hydrogen and the bicarb to get back to that homeostasis.